Hi everybody. So sorry you have to. I'm here again. This is a follow-on presentation of a different sensing project that we developed in our lab. So I'll skip the introductions. I didn't say before, but for those who are not familiar, this is Leeds and the Yorkshire Dales. Glasgow has been pretty stunning actually when I came up on the train line. If anybody's had the benefit of coming up on the train, but if you have chance, I'd highly recommend Yorkshire and Leeds. So you can see that's the university campus, and then some of the Yorkshire Dales. So if you get a chance, I'd highly recommend a visit to Leeds. So I mentioned before in the previous presentation about our magnetic sensing technology, and in the research project that we developed we started to kind of consider some of the limitations of that sensing modality. In particular, I suppose one of the things is magnetic sensing. It has an inherent sensitivity to environmental objects, so ferrous objects or magnetic sources that are placed near it, which could disrupt the signal or the measured signal. So we were quite interested in producing a sensing modality that would kind of move away from that and also look towards something where we could produce it in a more flexible form. So the magnetic sensing, it relies on this Hall effect chip being directly underneath the sensing node. So you have to position that element right underneath and right in the way of the force or the pressure that is actually being applied to the system. So there is some kind of degree of sort of physical robustness that you lose there. It also depends possibly on having like a fairly rigid substrate to put your elastomer on. So we're interested to see if we could kind of move towards something like a film technology, again at low cost, and use a different underlying transducer technique. So that was our motivation for this project. And we developed in our lab a tactile sensor. Here I'm just showing you the initial work on a normal force-based sensor, which uses the Eddy-Current effect. So this is widely used in industry for measuring precisely small displacements, and it looks at the a measurement of inductance between a coil and then a conductive layer, and there's some spacing between it. So if you measure the coupled inductance between those two, then you can derive the displacement between the underlying coil and then the top conductive layer. So in a similar way to the magnetic sensor, what we did is take a coil on a substrate and then place an elastomer between that coil and then the top conducting layer to modulate the applied force. And again, you can tune that elastomer layer so it can have different physical properties, either in terms of geometry or in terms of its physical compliance, to change the force sensing range that you'd achieve with this kind of sensor. It's quite applicable for fairly small systems. So here we've got a coil which is about 8 mil in cross section, but it could go smaller. It's more a limitation of our in-house fabrication facilities than anything else at this point. And we measure this coupled inductance using one of the new chips from Texas Instruments. So it's a digital inductance converting chip, which makes that whole package very convenient. But crucially, it means that this converting chip can be located further away from the actual sensing node. So we have our sensing coil where the applied force or pressure is, and then remotely we can have our sensing chip. So we were quite encouraged by this because it allowed us, we felt, to have something that was potentially more physically robust, but also we could maybe look at substrates which didn't necessarily have to be rigid anymore. So in this case, we've printed this system on a capped on film. So you can see in the bottom left the coils that we use. A standard industry kind of PCB fabrication technique, but applied to a capped on film enables us to bend the underlying substrate that the sensor is composed of. So we've mounted it on rigid plastic elements here for some calibration work, but inherently this could be bent, so this could be flexible. Not stretchable, but flexible. As I said, the advantages are there's no wires necessary in the sensing body itself, and we can accommodate a range of temperatures and apply forces to this system. It's fairly insensitive to contaminants, and the resolution and bandwidth exceeds the magnetic sensor that we developed. And last of all, but I think very importantly, it's easy to fabricate using mass manufacturing techniques at the moment. So we can produce these sensors, we can get these, we send away our designs and get them printed and they're sent back, but there's nothing particularly complex about the fabrication process for this Kapton film. It's just a double layer PCB. So we developed sensors for both normal force measurement, where you have the conductor and you just compress it, and you look at the coupled inductance between that coil and the conductor, and also shear force, which we'll come back to. And we were getting resolutions of about 0.115, 0.2 millinewtons in normal force. Again, it depends quite largely on the elastomer that you use, but that's kind of an indicative kind of value that you can achieve with this sensor. And just to give an example of the kind of the performance that we're achieving, again, brushing a feather across, you can clearly kind of pick up that kind of interaction. So it's very sensitive, but also physically robust. So here's our researcher tentatively at first hitting it with a hammer and then getting a bit more kind of motivated as it goes on. So we can run this at, say, 100 hertz and look at fairly kind of precise measurements, or we can run it very quickly and look at the same sensing body can determine things like a hammer strike and look at the range of force applied there. Also, just to kind of give an indication of its ability to work in different physical environments, and I guess in particular we're looking ahead towards towards application in the human body or with the human body. We've got this running, it's not particularly clear, but in a pot of water. So it's submerged there, and the sensor continues to operate within the water, and it can actually pick up the ripples as you kind of disturb the surface of the water. So in terms of application in the human body, like high humidity or physical robustness, they're obviously very important. So we're kind of encouraged by the underlying technology there. It did have one limitation, and that was that compared to the magnetic sensor, we weren't getting any shear measurements, and often that's quite important when you're interacting with things like soft tissues. You want to know not just the normal force, but the shear forces at the interface between those two objects. So what we decided to look at was having the conductor sit above more than one coil, and then we can look at the difference in inductance as that coil, again sitting on an elastomer, is displaced. So if you take your kind of your normal measurement where that conducting element is sat equally above all four coils, then you should have the same nominal inductance measured across each of those coils, or at each of those coils. As you apply shear, so we can see here it's moving from left to right, then the conductor is going to cover more of L3 and L4, and so there'll be a corresponding shift in the inductance seen at those coils relative to the to coils 1 and 2. So if we characterize that system, we've got 4 degrees of freedom in terms of the 4 coils, or the inductances at the 4 coils. Then we can pick up normal force and forces in shear, so Fx and Fy, by looking at the 4 inductance measurements from this system. So that's the basic premise of this work, really. Now we kind of suffer in terms of spatial resolution because all of a sudden we're jumping from a single normal force measurement and normal force coil to 4. So essentially our node now, our sensing node, is almost 4 times greater in area, but it does give us that additional, of those 2 additional degrees of freedom. And what we looked at, doing was a fairly simple sort of calibration where we can approximate the, we can try and normalize the system to some extent by looking at a combined kind of inductance measurement in the X plane by looking at L3 plus L4 minus L1 minus L2, and in a similar way Ly and Lz. So we're looking at a differential measurement there. So we fabricated the system, as you can see here. As I mentioned before, we put this on Kapton film, and you can see the kind of the dimensions of the system. Again, we're kind of working at dimensions really kind of constrained at this level by the manufacturing techniques that we had available to us at the time. I think we could shrink this down further, but this was easy to fabricate in our, with our facilities, and easy to operate in the lab environment that we have. And then we put an aluminium film on the top as a conductor. But interestingly, we've been looking at different shapes here. So at the moment we have a square, but you can consider different shapes and their effect. And we fabricated this and linked it to a single chip, which can make measurements of 4 different channels, which is very handy. So the outcomes of this system then, it's able to measure normal force as we did before, and you can see here we just had this on a lab setup where we applied normal force, then we applied shear, and then we stepped down, so we applied steps of normal force. So we kind of increased and increased and increased, and for each step in normal force we applied shear force as well. And the sensor was able to, with respect to a commercially available sensor from ATI, pretty accurately track the applied force in both normal and shear directions. And we're really encouraged by that. This is at low frequencies, I should say. So one of the inherent limitations that is built into this is the physical hysteresis effects that come from the elastomer. To some extent, you can see that as a design problem that you can tune for your particular application. If hysteresis, or if you need a high dynamic response, then you'd have to use something that was stiffer and that bounced back more quickly. So compared to something like the ATI sensor, it does suffer in that respect. But using this chip and this setup, we can sample up to about 1 kilohertz, and we're looking at force ranges of 0 to 20, 0 to 30 newtons, something like that. And the resolution that we're getting is about 0.3 millinewtons, or slightly below when you operate at 50 hertz. I should say that the kind of the measurement precision varies with the sampling frequency to some extent, because there's some smoothing that goes on in the inductance measurements. So looking at an applied example, so what do those kind of values mean? We stepped away from the feather for once, and we took a leaf back when the leaves were green on the trees, and ran that across the sensor, and it's able to detect both the normal force as the leaf drops onto the sensor, and also the serrations cause disturbances in the shear force. So it's accurate enough to pick up that kind of characteristic, that sort of signature. So it gives us quite a nice demo. And it brings us on to where we go in the future with this work. So it's at a point where this is our proof of concept. We've kind of piloted the work, and clearly there's a lot that can be done in terms of optimization. So we can explore fabrication techniques, which is a big interest to us. Also, the calibration of this kind of sensor. You can take a model-based approach, but it becomes quite difficult, and I think it's not particularly suited for that. So again, we're looking to use computational methods, nonlinear techniques. So we've used genetic algorithms before to characterize this kind of sensor, and then establish essentially a characteristic equation that we can then fit coefficients to for each particular model that we make. So we're looking to kind of extend that kind of approach to characterize these sensors. And also to expand these. So at the moment we have a single tactile. Again, we'd like to expand that and to cover a larger area. And last but not least, obviously look at their application in healthcare. So I'll just finish up by again thanking my collaborators, my colleagues, who are fantastic to work with and have done a fantastic job on this. If you'd like to speak to me, I'll be around over lunch. I've also got a demo unit of the compliance sensor if you'd like to have a look, see it in action. More than happy to discuss that. And if you have any kind of ideas for collaboration, always happy to discuss. Thanks very much.